Welcome to section 2.3 in pre-calculus. This is the section on quadratic functions. So a quadratic function is a function of the form ax squared plus bx plus c, like this. Alright, so you're always going to have an x squared term, but occasionally, depending on the function, your b will be 0 or your c will be 0, and you'll just have a squared term. But in order to be a quadratic function, you'll always have a squared term. So that is this meaning here. A is never going to be 0. All right? So the domain of a quadratic function is all real numbers, written as negative infinity to positive infinity in interval notation. So if your coefficient A is positive, you'll have an upward-facing parabola. If your coefficient is negative, you'll have a downward-facing parabola. Now let's talk about standard and general form of the quadratic function. So the general form of a quadratic function is the one we just talked about here, where it's written out like a polynomial, and your leading coefficient is never 0, meaning you're always going to have an x squared term. That's the general form when it's written like a polynomial. Standard form, also sometimes called vertex form, is written in what you're used to seeing now after our transformation studies in this format here, where you can see where the horizontal shift is inside the parentheses, the vertical shift is outside the parentheses, and then your dilation or contraction factor is in front. So this is vertex form or standard form of a quadratic function. All right. So theorem 2.2 says they're calling it vertex formula, vertex form, whichever one you want to use, for a quadratic that looks like this. From here, we're going to interpret that the vertex is this number h, that's your x coordinate, and this number k, that's your y coordinate of your vertex. And we're going to study how to get from standard general form of a quadratic equation to convert it into vertex form. Another thing that we're already familiar with from prior studies of quadratic equations is that the zeros, sometimes called the solutions, sometimes called the x-intercepts, are gotten by the quadratic formula. So here's the quadratic formula right here. And by the time you get into pre-calculus, you've seen it in Algebra 1, you've seen it in Algebra 2, and now you're going to see it in pre-calculus. This is something that you should know off the top of your head. So go ahead and write it down in your notebook and try to make sure that you've got it memorized. So if I look at a sketch of a quadratic function, your x-intercepts are these places right here where your graph crosses the x-axis. So those are called your zeros, your solutions, or your x-intercepts. You can calculate those dots for any, those solutions I should say, for any quadratic equation by using the quadratic formula. Okay? All right, let's take a look at this graph here of a quadratic. So let's make a few notes here. The domain of this quadratic is always going to, for any quadratic, is always going to be all real numbers in interval notation. We would write it like that. The range, however, is different. It's got a lowest point here, and that lowest point is right here, and we could read it off the graph here. It looks to be -9. Okay, so the graph here only exists, this picture here, above -9. So when we're writing our range, we go lowest to highest. So when writing our range, we would have a square bracket for that point down there at -9. That's our lowest y value. And we would keep going. Imagine there's arrowheads on here to positive infinity in the y direction. Now let's talk about increasing and decreasing intervals. So we're going to look at this point here as being the separation between the increasing part of the graph and the decreasing part of the graph. So here we're going downhill left to right. That would be decreasing. Then we turn around at the bottom there of the lowest part of the graph, and then we go uphill. That's increasing from left to right. So if I'm going to write that in interval notation, I go left to right. So I'm looking at my x values here where I've cut this right down the middle, and reading it off the graph, that's an x value of -2 where it turns around. All right, so if I do increasing first, I'm going to start at -2, and I always use a smooth bracket when I'm describing increasing and decreasing intervals. I start at -2, and I increase forever and ever and ever in the x direction. Now when I talk about decreasing left to right, I start at negative infinity. That's as far to the left as I can go, and I decrease all the way until I get to -2, and that's where I turn around. That's my decreasing interval. Smooth brackets as well. So let's talk about the vertex. So the vertex, of course, is this point right here. All right, and that's the lowest point in this particular parabola. So the vertex, the coordinates, you would give it as a coordinate pair, is -2, -9. While we're at it, let's talk about the x-intercepts and the y-intercept. There'll be one y-intercept here. All right, so the x-intercept are the places, like we just said earlier, where you cross the x-axis. So I've got one there at 1, x value of 1, y value of 0, and one here, x value of -5, y value of 0. So I'm going to write those here. Sometimes in your homework you'll notice that they ask you to put them in lowest to highest order or left to right order. So watch out for when they specify that. And then the y-intercept, of course, would be the place where it crosses the y-axis, and that would be the point x is 0, y is -5, and I'm reading that directly off the graph. So be on the lookout for whether they're asking you for the ordered pair or how the question is worded. All right, this example says graph the following functions, starting with the graph of the parent function f of x is equal to x squared and using transformations. Then find the vertex, the range, and the x and y intercepts, if any exist. Okay, so we've got g of x here in vertex form. So I'm going to graph that in the transformational method. So first I'm going to put on my graph, the graph of the parent function. And then I'm going to choose 3 points on my parent function that I'm going to transform. So I'm going to take the vertex, and I'm going to take the point 2, 4, and the point -2, 4. And I'm going to transform those 3 points and redraw my function. All right, so I wrote those points down. Now, what you recall from what we learned in the last unit was that if you have a +2 inside the parentheses, that means I'm going to shift to the left by 2. So that means each x-coordinate I'm going to subtract 2. Subtract 2. And then if you have outside of the parentheses a vertical shift, you use the sign of the number there. So this is a down 3 vertical shift, and that happens to the y-coordinates of your parent function. So if you did have a factor out front here, you would multiply the y-coordinate first and then subtract 3. But since this is just a 1 here, the only thing we need to do to transform the y-coordinate is subtract 3. So 4 minus 3, 0 minus 3, 4 minus 3. So there's my graph of my transform quadratic. So now let's find the vertex. So the vertex is here. So the coordinates of the vertex, let me just call it V, are -2, -3. Those you can also get from these two numbers here. Opposite sign for the x-coordinate, and then this is your y-coordinate of your vertex. Next, we're going to state the range of the function. So the range is the y-coordinates that, let's see why my pointer isn't working, the y-coordinates. So everything above the lowest point on our graph will lie on our curve. So -3 is the lowest point. So if I call my range R for range, well, I'll just write range. My lowest point, square bracket, -3. So that -3 is on the graph. That's why I have that square bracket. So lowest to highest, so that's lowest y. Highest y would be positive infinity round bracket. So the infinities always get a round bracket. Right, so that's my range. All right, now let's find the x-intercepts. So to do that, we have to find the solutions or the zeros, which in this case might require either factoring or using the quadratic formula. Now to see whether you can find the x-coordinates by factoring, let's expand x plus 2 squared. So this is x plus 2 squared, and then we have -3. So that's x squared plus 2x plus 2x plus 4 minus 3, which is x squared plus 4x plus 1. Now I can't factor that because the only way to multiply to get 1 is 1 times 1, and then you won't be able to add to get 4 using a 1 and a 1. So I'm going to have to use the quadratic formula. Now remember, I'm going to tell you guys to write this down a few times as we're going along in this unit, and hopefully by that point you've got it memorized. So -b plus or minus the square root of b squared minus 4ac all over 2a. All right, so a is 1, b is 4, and c is 1. Okay, so we're going to plug those in. Let's write it over here. A is 1, B is 4, C is 1. Okay, so we have to do it in that order. Now we're going to substitute. So our x's are going to equal to -4 plus or minus the square root of b squared minus 4 times a times c divided by 2 times a. So that's -4 plus or minus, so that's 16 minus 4, that's 12, divided by 2, which is equal to -4 plus or minus 2 root 3 over 2, which is equal to -2 plus or minus root 3. And this is all stuff you've learned back in Algebra 2. So wait, let me get rid of that, hold on. Let's do it here. So if I divide out by 2, I can reduce this fraction here, here, and here. Okay, so these are going to be my x-intercepts right here. So let me just make some room for myself here. Okay, so your x-intercepts are these points right here and right here. And these are going to be decimal numbers. They're not landing right on the tick marks, which can sometimes happen in real life. But if you plug in, let's get these in decimal form. Let me just show you how to do that. I'm going to have two x values, -2 minus root 3, and I'm going to have -2 plus root 3. So negative 2 minus root 3 is negative 3.732, and negative 2 plus root 3 is negative 0.268. So those are these 2 points here. This would be the negative 0.268, and this is the negative 3.732. So if you're going to write those as coordinate pairs, the one furthest to the left is negative 3.732. That's your x coordinate and your y coordinate. And then you've got negative 0.268, comma 0. So those are your x-intercepts. Now for the y-intercept is just the place where the graph crosses the y-axis. So it's this point here, which looks to be 0, 1, because we figured that out in the transformation. But the other way to figure it out is to find out what g of 0 is. When the x coordinate is 0, or the value of x is 0, I've got 0 squared plus 4 times 0 plus 1. So that's equal to g of 0 is equal to 1. So our y-intercept is the point x0, y1. So this is our y-intercept. Okay, so we've taken care of that problem. Now let's look at problem number 2. I'm going to take the same 3 points and transform them according to the second equation. So the second equation says we're going to the right 3, and then we're multiplying the y coordinate by 2, and then adding 1. So let's do the x's first. So the x, we're going to the right 3, so that means we're going to add 3. And then for the y coordinate, we're going to multiply by negative 2 and add 1. So we've got 4 times negative 2 is negative 8. Negative 8 plus 1 is negative 7. And then for the second one, we've got 0 times negative 2 is 0. 0 plus 1 is 1. And then for this one, I've got the same number here because it's also a 4, so this would be negative 7. So if I put those points on the graph, there's my graph. So it's a downward facing parabola, which makes sense because I've got this negative sign here in front. All right, it's narrower because I've got this 2 here, and then it's shifted to the right 3 and up 1. Okay, so now let's go ahead and write the vertex. So my vertex, I'll just call that V, is the point 3, 1. All right, then the range. Okay, so I've got a square bracket for my highest value. My highest value is 1, and then this time it's beneath 1. So, wait, I'm going in the wrong order here. I have to go from lowest to highest. So lowest to highest, this way, is negative infinity, smooth bracket, all the way up to 1 square bracket. So you got to make sure you get the range in the correct order. So I have to go from lowest, which is negative infinity, round bracket, to highest y value, which is 1 square bracket. Okay, now let's find the x and the y intercepts. You can see that the graph is going to have x-intercepts in 2 places here. So we've got to calculate those. So what we want to do first is expand out the function. So I've got negative 2 times x minus 3 times x minus 3 plus 1. So I've got negative 2 times x squared minus 3x plus 9 plus 1, which is negative 2 times x squared minus 6x plus 9 plus 1, which is negative 2x squared plus 12x minus 18 plus 1, negative 2x squared plus 12x minus 17. Okay, so let's go ahead and use the quadratic formula on this as well. And I'm just going to say this doesn't look too factorable to me. Of course, the way you would tell is to multiply negative 2 times negative 17, so that would be 34. So we've got 1 and 34 and 2 and 17. There's no way to add or subtract to get you a 12. So we're going to have to use the quadratic formula. All right, so let's make some room. All right, so I rewrote the function. Now in this order, we've got a is negative 2, b is 12, and c is negative 17. So using the quadratic formula, I've got negative b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. So that's negative 12 plus or minus, that's the square root of 144 minus 136 all over negative 4. So let's go over here. So that's negative 12 plus or minus the square root of 8 divided by negative 4. So that's equal negative 12 plus or minus 2 root 2 divided by negative 4, which can be reduced by a factor of 2. So reduce it when you can. So that's equal to negative 6 plus or minus root 2 divided by negative 2. And then you want to go ahead and cancel those negatives. So I've got 6 plus or minus root 2 over 2. Okay, so these are my x coordinates. Now if I type those in, and I've got 6 minus root 2 over 2, so I went ahead and punched that in to the calculator, and I've got 2.293, rounded to 3 decimal places. So one of my x-intercepts is this, and the other one is 6 plus root 2 all over 2, and you would get 3.707 if you typed it in. That's my other x-intercept. Okay, so that's these 2 points right here. Those are your x-intercepts or your solutions. Now I am going to have a y-intercept somewhere where it crosses way down, further down the y-axis. Now the way that you're going to figure that out is to take your function negative 2x squared plus 12x minus 17 and substitute 0 in for x. All right, so this is h. Our function is h here. H of 0. H of 0 is, let's neaten that up a little. H of 0 is cancel, negative 17. So it is going to cross down here at the point 0, negative 17, which is off my graph. So that would be your y-intercept. Okay, so we figured all that out. All right, next. Okay, we're going to learn something a little new here called completing the square. And the reason we need to learn this new technique is to transform from general form to standard form, sometimes called vertex form. Okay, so the technique completing the square, I'll just go ahead and write it. And the reason it's called that is because we're basically relying on the pattern that let me just show you real briefly what I'm talking about. Let's say you had x plus 2 squared. Okay, so that's a squared binomial, the binomial being x plus 2. So x plus 2 times x plus 2 is x squared plus 2x plus 4. which is x squared plus 4x plus 4. All right, so the pattern I'm talking about is in order to go from this here form, which is called a perfect square trinomial, to this form here, you take the square root of this term and put it here, and the square root of this term and put it here, and this sign and put it here, and then you put your little square here, and you're back to this here. So if you follow that pattern, you could go from the perfect square trinomial to the factored form of the perfect square trinomial, which is a binomial squared. And that might look kind of familiar because when you've got an equation in vertex form, this is simply your right translation, your right-left translation, and then whatever you have over here is your vertical translation. So it comes in real nice when we're trying to figure out what our left-right translation is. So the next question is, how do we do it? Okay, so the way that you do it is you take your original quadratic, in this case it's x squared minus 4x plus 3, and then you write it like this, x squared minus 4x, my two x terms. You insert a blank, which we're going to use to form our perfect square trinomial. Then you've got the plus 3, and then you insert a second blank, which we'll use to take out the number that we put on the first blank, so we really haven't altered the original balance of the equation. All right, so we're going to engineer this perfect square trinomial. So the way that we do that is we take the middle term, cut it in half, and square it. So that's 2 squared, which is 4. Then I put that here. As you can see, it now looks like that perfect square trinomial that we had that I was showing you earlier. All right, so if I put plus 4 there, I'm going to put minus 4 over here. That way 4 minus 4 is 0, and I haven't changed the balance of my equation. All right, now I can go ahead and utilize my knowledge of the pattern to write the perfect square trinomial in factored form. So you take the square root of this one, and you use this sign here. So the square root of x squared is x. The square root of 4 is 2, and then the minus goes in the middle. All right, so we've done it. We've used our knowledge of how to factor a perfect square trinomial. And then the numbers, the loose numbers, you just combine. So we've got 3 minus 4, that's negative 1. All right, so this is the equivalent form of f of x written in vertex form. So if I put that on a graph, I need my vertex first. So from here, you get your vertex. Let me write vertex by looking at your translation. So it's right to, so my parent function 0, 0 is going right to, so my x-coordinate would be 2, and my y-coordinate would be negative 1. So we get that directly from the vertex form. So I put my vertex on my graph. I've got 2, negative 1. Okay, so this is the upward facing parabola. Let's get the y-intercept so we can draw it more accurately. So the y-intercept you would get by finding f of 0. So that would be 0 squared minus 4 times 0 plus 3, which is 3. So the y-intercept is the point 0, 3. All right, so now I can get a little better sketch here. All right, so that's my sketch of my quadratic. Now let's go ahead and clean this up a little bit. Okay, next let's find the x-intercepts. So I'm going to try to factor my quadratic and see if I can do it the easy way. If I can't, then I've got to use quadratic formula. So I've got 1 times 3 is 3. So there's one way to multiply to get 3. I need to add to get negative 4. So if I put two negatives on, I can multiply to get positive 3 and add to get negative 4. So that means I can do it the easy way. So the factored form will simply be put the minus 1 here and the minus 3 here. All right, so x minus 1 equal to 0. That means I've got an x-intercept of 1, 0. Over here, x minus 3 is equal to 0. I have an x-intercept of 3, 0. All right, so that's here and here on my graph. Those are my x-intercepts. And then we found our y-intercept here. All right, the next thing it's asking for is the range. So the range, lowest to highest, would be square bracket. So range, square bracket, lowest y value is negative 1. Highest y value is positive infinity. All right, and the last thing, the axis of symmetry, which is the imaginary line that cuts our parabola right in half, such that if you fold it on that line, the left-hand side will exactly cover the right-hand side and vice versa. So the equation, let's just call that the AS, axis of symmetry, is the vertical line x is equal to 2. So we write the axis of symmetry as a linear equation. X is equal to 2. Okay, so one more example of these. Okay, number 2, I'm going to do the same thing. So I need to reorder that equation such that my x squared term is first. So negative x squared minus x plus 6. All right, so I want to, in order to complete the square here, I want to take this negative sign out, factor it out of the x terms only. So I'm going to have negative x squared plus x plus blank plus 6 plus my balancing blank. Okay, so I did not change the sign on the 6. Okay, I want to leave that alone. All right, so I can see if I distribute that I've got minus x squared minus x plus 6, these here, nothing there yet. So it's still this. All right, so now I'm going to take my 1. I'm going to divide it in half and square it. And that's going to give me 1/4. Because 1/2 times 1/2 is 1/4. All right, so I've put in a minus 1/4, because if you think about this as distributing, this goes here, here, and here. So if I added in a negative 1/4, I need to get rid of that negative 1/4 by putting in a positive 1/4 over here. All right. So now let's go ahead and use our pattern knowledge. Okay, so the square root of x squared is x. The square root of 1/4 is 1/2. The sign is plus. And then if I add 6 and 1/4 together, I get 6 plus 1/4. I need a common denominator, so that's 24/4 plus 1/4. That's 25/4. All right, so 25/4 is the same thing as 6 1/4, 6.25. So my vertex, let's just call it, well, we'll call it vertex. Vertex is negative 1/2, opposite sign for the x, and then 25/4, or you could call that negative 0.5, 6.25 for help with the graphing. So negative 0.5, 6.25, and then it's a downward facing parabola. So let's see where it cuts the y-axis. The y-intercept would be g of 0. That's 6 minus 0 squared, which is 6. All right, so it's cutting through. This is your vertex. So it's going to have x-intercepts somewhere, and we've got to calculate those. Okay, so we use the vertex form to find the vertex, to graph the function, and now we're going to figure out what the x-intercepts are. So the way that we do that is we factor it if we can. If we can't factor it, then we use the quadratic formula. Okay, let's try to factor this. So you never want to factor with a leading negative, so we're going to factor out the leading negative, which changes the signs on the other terms. Okay, so positive, positive, negative, that changed all the signs on the original equation. All right, so I've got a 1 times a negative 6. So there's two ways to multiply to get 6. 1 times 6 and 2 times 3. So I need to add to give my middle coefficient, which is positive 1. So if I put a negative here, negative 2 times 3 is negative 6. Negative 2 plus 3 is 1. So I'm going to choose these two numbers here. Since I've got a leading coefficient of 1, I can do it the easy way. I can just say plug in this negative 2 for the first factor and the positive 3 for the second factor. You can verify that that always works as long as you have a leading coefficient of 1. Remember, if you don't have a leading coefficient of 1, you have to factor by parts. All right, so x is equal to 2, x is equal to negative 3. So our x-intercepts are 2, 0, and negative 3, 0. So this one here would be your negative 3, 0. This one here would be your 2, 0. All right, so we've done everything except for the axis of symmetry. So the axis of symmetry goes through the vertex, and it cuts your quadratic right down the middle, right down the center line. So it must go through the x-coordinate of the vertex, which in our case was negative 0.5. So the equation for this vertical line is x is equal to negative 1/2, or it's also equal to negative 0.5. So this is the equation of the vertical line. This is your axis of symmetry. Okay, so we've done these two problems, completing the square. Okay, this problem says consider the function 2x squared plus 7x minus 15. Find the x and y intercepts and the vertex. Okay, so let's find the x and y intercepts by trying to factor this. So I've got a 2 times a negative 15. I have a negative 30. The ways to multiply to get 30 are 1 times 30, 2 times 15, and 3 times 10. So they need to add to give positive 7, so I do need to have a negative on the 3 here. So if I add this, negative 3 plus 10, I get 7. If I multiply, I get negative 30. So I can't do the easy, just plop those in the parentheses because I have a leading coefficient of 2, so I need to factor by parts. So let me rewrite my equation. This is a technique you should know already. All right, so 2x squared. Now I'm going to replace my 7x in the middle by negative 3x plus 10x minus 15. And I'm going to factor this by parts. So the GCF of the first two terms is x times 2x minus 3. I'm going to bring down this sign here. The GCF of 10 and 15 is 5. And I'm going to bring this 2x minus 3 over here. And like I said, this is a technique you should have learned in Algebra 2. All right, so now when I factor by parts, I've got 2x minus 3 times the other parentheses will have the x plus 5. And you can go ahead and verify that on your paper that if you distribute these two binomials, you will end up with the original quadratic function. So since it's factorable, we can easily get the x-intercepts. So from the first one, I've got 2x minus 3 equal to 0, which is 2x is equal to 3, which is x is equal to 3 over 2 or it could be written as 1.5. And then from here we've got x plus 5 is equal to 0, or x is equal to negative 5. All right, so our x-intercepts are 1.50 and negative 50. Those are our x-intercepts. Okay, so let's put our graph over here. Okay, so I put my x-intercepts on. Now I can see that my graph, because my leading coefficient is a positive number, is going to be an upward facing parabola. But for accuracy, I'm going to find the y-intercept before I sketch my graph. So you find your y-intercept by finding f of 0. So that's 2 times 0 squared plus 7 times 0 minus 15, which is equal to negative 15. So my y-intercept is the point 0, negative 15. So it's way down here. So let's just say this is my point 0, negative 15. All right? So if I sketch my graph, it's going to go like this. All right? So my vertex is down here. All right? Now I'm going to use a different technique for finding the vertex, and this is another way of doing it. Since we know that this is your axis of symmetry that goes right through the vertex, you know that this distance, let's do it in a different color, you know that the distance between this x-intercept and your axis of symmetry is going to be equivalent to this distance here. Okay? So the fact that we know that this one is at 1.5 and the other one was at negative 5, if we can find the average of those two numbers, then that'll tell you what the equation for your axis of symmetry is. So in order to take an average, I add the two numbers up and divide them in half. So the average then is negative 1.75. All right, so that's my axis of symmetry. X is equal to negative 1.75. Now, of course, that's also the x-coordinate of my vertex. Okay? We're also asked to find the vertex here. All right, so from there, if that's the x-coordinate of my vertex, I now can find the y-coordinate of my vertex by plugging negative 1.75 in for x. All right, so let's scoot it up a little. So I've got 2 times negative 1.75 squared plus 7 times negative 1.75 minus 15. Let's see, and that is negative 21.125. That's the y-coordinate of my vertex. So negative 21.125. All right, so this point down here would be negative 1.75, negative 21.125. Okay, so that's the lowest point on my graph. All right, so we've done that one. Okay, next example says consider the quadratic function shown. Find the x and y intercepts. We'll do that first. Okay, so the way to find the x-intercepts, you want to check to see whether it's factorable. So let's check and see. So I've got a 1 here, and 1 times negative 32 is negative 32. So we've got 1 times 32, 2 times 16, 4 times 8. So we got to multiply to give negative 32, so we need 1 negative. We've got to add to give positive 4, so the negative would go here. So since we've got a leading coefficient of 1, we can jump to our factored form by putting negative 4 in the first set of parentheses and 8 in the next set of parentheses. Okay, to find the x-intercept, we just solve the equation. So x is equal to 4, and x is equal to -8. So our x-intercepts are 4, 0, and -8, 0. To find the y-intercept, we just find f of 0. So f of 0 is 0 squared plus 4 times 0 minus 32. So the y-intercept is the point 0, -32. All right, so that's a start on our graph. So I'm going to make a little sketch. So my y-intercept is 0, -32. I've got an x-intercept of 4, 0, and an x-intercept of -8, 0. Okay, so you would probably want to make a much neater graph than this. All right, now that, let me redo that a second. Okay, I'm not going to graph it yet because I want to show you how to find the vertex from vertex form so we can practice completing the square. Remember, on the last problem, we could also take the average of the x-intercepts and use that x value to find the vertex, but I'm going to do it by completing the square this time. Okay, so I'm going to convert to vertex form by completing the square. So I've got x squared plus 4x minus 32. All right, so I've got to put my blanks in first. So I've got x squared plus 4x plus blank minus 32 plus blank. So I take my middle term and I cut it in half and I square it. So that's 2 squared, which is 4. And then I put the positive 4 there. That's going to be always positive because whenever you square something, it makes it positive. And so that's why I ignore this sign when I'm coming up with this number here, because it's always going to be a positive number. All right, so this is positive, which means if I take it out, this would be negative. So net 0, 4 minus 4, that's what we want. Okay, so now I do my pattern. I know it's going to end up looking like this. All right, and I know that I've engineered this perfect square trinomial such that when I factor it, it'll look like this. So I take the square root of this, and then I put the plus here. So plus. All right, so the square root of x is x. The square root of 4 is 2, so that looks familiar from one of the other ones we did. All right, and then combine the two loose terms, and I get -36. All right, so f of x rewritten in vertex form is this. So from there, I can readily get my vertex. So my vertex is opposite sign of 2 is -2, all right, and -36. All right, so -2, -36, that's my vertex. Just put a V beside that. All right, so if I sketch that graph, now I strongly recommend if you do have graph paper that you use it just so that you can do a neat job with your graphs so you can understand them better. All right, so I've got my vertex. So I did part A, I did part B. My vertex is an ordered pair, that's part C. Now I'm going to write the equation of the axis of symmetry. So that's my vertical line through my vertex. So it went right through x is equal to -2. So the equation is x is equal to -2. So this right here is my equation for my axis of symmetry. And I graphed the function. So we're finished with this problem. Let's go on to the next one. Okay, so the reason I put this problem in here is because it's missing the middle term, so it might throw you a little bit. So I've got this equation f of x is equal to 4x squared minus 25. It's clearly a quadratic because it has an x squared as the highest order term. Okay, it's just missing the middle term, so we interpret that as meaning that the b is equal to 0. So I want to write that equation in vertex form. Okay, so in a way that's kind of a trick question because we don't really need to complete the square because there's not an x to the first power term. So you can think about it as 4 times x minus 0 squared minus 25 if you like. But really, when you don't have an x term, there's not really an alternate form of the equation. Okay, so from there, I can get my vertex directly as 0, comma, minus 25. Okay, so there's no left-right translation when you've got that 0. So there's my vertex. However, I do have that 4 in front, so that's a vertical stretch. Okay. So I've got the vertexes in ordered pair. Now we want to find the x and the y-intercepts. So we're going to factor this equation to find the x-intercepts. So let's take a look at that equation over here. So 4x squared minus 25 is special in a certain way, so you might want to pause this video and think about it for a minute before I tell you why it's special. So I hope you thought about it for a second. It's special because this is a perfect square and also this is a perfect square. So we have an easy way to factor the difference meaning a subtraction of two perfect squares. And if you recall from learning how to factor in Algebra 2, that the factored form is 2x, 2x, 2x being the square root of 4x squared. Let's just write that here. Square root of 25 is 5. And then 5, 5. Now pause this video again and see if you can remember what it is about the signs that we learned. All right, so I hope you thought for a second and remembered that you have a positive sign and a minus sign. One way to help you remember that you have one of each sign is that the middle term would cancel out, so you'd have a plus 10x minus a 10x, so therefore you'd have no middle term left. They'd cancel each other out. So the factored form of a difference of two perfect squares is always going to have this look to it. From here, we can find the x-intercept by setting it equal to 0 and solving each of these factors. Set equal to 0. And we've done this many times, so this probably doesn't seem one bit strange. So I'm solving for 0 there. And I'm going to do the same thing, but you can see it's going to be positive this time. Okay, so my x-intercepts are, we can call that negative 2.5 if you'd like, negative 2.50 and 2.50. All right, now my y-intercept is f of 0, so you can see that f of 0 is going to be 0 minus 25, which is minus 25. All right, so your y-intercept is then the point 0, negative 25. Okay, so now let's make a little sketch here. As you've probably realized, this quadratic is symmetric with respect to the y-axis. So my y-intercept is also the vertex. Okay, and then I've got 2.50 for this x-intercept and negative 2.5 for that one. And then I sketch it in. And that is symmetric with respect to the y-axis. So my axis of symmetry then would be the y-axis itself, which is the equation x is equal to 0. Okay, so we've done this problem. Let's go on to the next one. You will notice in your when you get to your problem set that you've got a couple of application problems, sometimes called word problems. So I thought I would go through a couple of those for you. These kind of problems having to do with projectiles are very, very common in calculus, so it's good to get a little bit of practice with them here. So it says we have a launcher perched on top of a 48-foot tower. We launch a projectile vertically upward, and it says the height of the projectile at any time t after launch is given by this function h of t. H is a function of time, is equal to this function here. So it's got a parabolic path, a flight path for this projectile. So the questions are, what is the height of the projectile at time t is equal to 0, the time of the launch? So let's answer that question first. So for part A, when t is equal to 0, we just want to find h of 0. So I'm going to substitute 0 in for time. And I'll get, this is going to go to 0 here and here, so I'll get 48 feet. All right, and that intuitively makes sense because it hasn't taken flight yet. Basically, it's just getting ready to, so the assumption here that it's at an elevation of 48 feet. All right, so that's the answer to question A. Question B says, what is the maximum height of the projectile and what is the time when it reaches its maximum height? So I make a little sketch here. So if it starts out at 48 feet, it's going to fly through the air vertically upward. Then it's going to turn around at some point because of gravity and fall to the ground, like a missile launch, okay, or throwing a ball up in the air, something like that. Okay, these are very common problems. So this is 48, and at some point right here, we're going to reach our maximum height at a certain t, I'll call it max time, t max. Okay, so part B says, what is the maximum height of the projectile and what is the time when it reaches its maximum height? Well, you can see in the picture that that would be your vertex there, your highest peak, your vertex of your parabola. Okay, it's an upside down parabola. Hence, that is why you've got the negative in front of the 16t squared. All right. So one strategy we can use for these kinds of problems is our knowledge of the axis of symmetry. Okay, so if that red line I drew there is the axis of symmetry, and that corresponds to the peak of the parabola, then this point where it hits the ground is one of the x-intercepts, and this point over here, this invisible point, which doesn't really play into it physically, would be the other x-intercept of our upside-down parabola. So if I factor my parabola, I should be able to find this imaginary point over here, which doesn't have any physical meaning in our projectile problem. That would be one x-intercept, and this would be the other one. And the time t max would be the average of those two values. Remember, our function is written in terms of t being the independent variable and h being the dependent variable. So right here, instead of y, we've got h. Instead of x, we have t. All right, so I'm going to go ahead and I'm going to try to factor this equation. If it's factorable, then I won't have to use the quadratic formula to find those two x-intercepts. So I'm going to say I've got negative 16t squared plus 52t plus 48. I want to factor out that negative, and I can see that I also have a GCF of 4. For all these numbers here, I can take 4 out. So I see that would be 13, and this would be let's see, I got to change my sign. Let me put my 12 here. I'm factoring out a negative, and that's going to cause all of my signs to change. So this is negative, and this is negative. So I'm going to check it. So I got negative 4 times 4t squared. That's okay. Negative 4 times negative 13t. That's okay. Negative 4 times negative 12, and that is also okay. So this is another form of this, and this is how you would want to factor it. So let's see if that's factorable. So 4 times negative 12 is negative 48. So I've got 1 and 48, 2 and 24, 3 and 16. Okay, I think I hit on it there. 3 and 16. That multiplies to give you 48. If I need one negative to multiply to give negative 48, I would want to put my negative on the 16, such that when I added 3 plus negative 16, I would get my middle term, negative 13. So these are my two numbers here. So, but notice that I can't just put them in the parentheses because I've got that leading coefficient of 4. So I'm going to leave the, okay, so I can't just put in my 3 and negative 16 into the parentheses because I've got to factor by parts because of this 4. So let's go ahead and factor by parts. And I'm going to leave that GCF of negative 4 aside for a minute. So I've got 4t squared plus 3t minus 16t minus 12. All right, so that means I'm going to factor out a t here. So I've got 4t plus 3. I'm going to bring down my negative, and I'm going to factor out a 4 of 16t, factor out a 4 of minus 12. So this is just going to repeat over here, plus 3. All right, you want to check that and make sure you didn't mess up. So 4t squared, 3t, negative 16t, and negative 12. Looks okay. So now I've got 4t plus 3t minus 4. All right, so it was factorable, so I can find my x-intercepts. So this is t is equal to negative 3/4. So that would be this dot over here. So, all right, and this one here would be t is equal to 4. So this x-intercept is 4, 0. Okay, so that means that if I wanted to find t max, I would take the average of negative 3/4 and 4. Before I go on, I just want to mention when you've got x-intercepts, this leading coefficient here does not change your x-intercept. It just changes the shape of your parabola. It's still going to have the same x-intercepts. All right, so I'm going to find out what the average of negative 3/4 and 4 is, and that's going to give me my axis of symmetry value, my t max. So you would just add negative 0.75, that's negative 3/4 plus 4, and divide that in half, and you get 1.625, and that would be seconds. Okay, so T max is 1.625 seconds, the time when your projectile reaches its maximum height. Now, to figure out the corresponding height, you would just substitute 1.625 into your equation. So you're basically finding h of 1.625. You're evaluating your equation at 1.625 seconds. So you can go ahead and do this in the calculator, obviously, right? And I'm going to go ahead and just write this out for you. And then plus 48. All right, so if you go ahead and put that into the calculator, you're going to find out that your max h, and I'll just call it h max, is going to equal 90.25 feet. So that's the height it reaches before it turns around and starts heading down toward the ground. All right, so part C, what is the time when the projectile hits the ground? Okay, so we kind of already figured that one out. That's your x-intercept 4, 0. So when it hits the ground, the elevation is 0. Your h value is 0, which corresponds to a time of 4. Okay? Okay, here's one more type of word problem which is very common with quadratics because it's an area problem, which is a squared function. Okay, so this says here that Skippy wishes to plant a vegetable garden along one side of his house. In his garage, he found 32 linear feet of fencing. That means if he stretches out his roll of fencing, he has 32 feet of it. Since one side of the garden will border the house, Skippy doesn't need fencing along that side. What are the dimensions of the garden which will maximize the area of the garden? And what is that maximum area of the garden? So I made a little sketch. So this is the wall of the house. So his garden comes out from the wall, and we'll call this side of it W, W and W. So we've got two W's for width, W for width. And then we've got the length of the garden here, L. All right. So the perimeter of the garden, let's just call that P. The perimeter is equal to W plus L. It's three sides. All right. So that's the same thing as 2W plus L. So we need to have enough fencing, and he has 32 feet of it, and he would want to use it all to go from here, here, and here. So perimeter would be 32 feet. So that means 2W plus L is 32 feet. So I can say L is 32 minus 2W. All right, so then he wants to maximize the area of the garden, so we need an expression for area. So area is equal to, there's a rectangle, so it's L times W, length times width. All right, so area would be equal to, so we have an expression for L in terms of W, so we can get this all in terms of one variable, and it looks like we can replace L with 32 minus 2W. Because right here, L can be replaced with 32 minus 2W. So here's L. I'm going to call it 32 minus 2W. All right, so here's W. I need to put that beside it. It's multiplied together. So if I distribute that out, I'll get 32W minus 2W squared. Now you can see why this kind of a word problem is a part of a quadratic unit, is because that's a quadratic expression. The highest degree, the highest powered term is a 2. That's a quadratic expression. All right? So now what we want to do is organize that A expression. Let's put the highest degree term first. So minus 2W squared plus 32W. So we have this equation here. So we want to find out where this equation reaches its highest value. Because it has a leading negative, that means it's an upside down parabola. All right, so let's make a little graph of this thing. So let's find out what the x-intercepts are, and then we could make a sketch. All right, so if I factor this, I'm going to take out a negative 2, so I'd have W squared minus 16. Well, I can take out a W too, so let's put a W right there as well. So I need to erase this 2 here. So I've got negative 2W times W minus 16. And we want to check and make sure that works out. Negative 2W times W is negative 2W squared. Negative 2W times negative 16 is positive 32W. All right, so that works. Now let's from here find out what the x-intercepts are. So we're going to set it equal to 0 and solve each of these factors set equal to 0. So minus 2W equals 0. That means W must be 0. All right, and then here W must be 16. All right, so let's erase. Well, I'll just scoot it up a little. I'll just put it over here. So I've got an x-intercept of 0 and an x-intercept of 16. All right, so this one's at 0. All right, so already we know something might be fairly easy to figure out. Halfway between 0 and 16 is 8. All right, and this is going to be an upside down parabola. So somewhere up here is going to be my vertex, my highest value. That's my max right there. All right, this would be my axis of symmetry. Okay, so that worked out pretty easily because one of them was at 0. Half of 16 is 8. All right, so that means this is my W axis. So let me just make a note of that over here. This is my W axis, and this is my area axis, because my function is in terms of W, A of W, because you can see here that I've got a W instead of an X, and I've got an A instead of a Y. All right, so I know that my W at my peak is 8. So the width of this garden must be 8. So if the width is 8, that means the length must be, let's figure out the length, 32 minus 2 times 8. So that's 32 minus 16, that's 16. So the length must be 16. So that means my area then, which is something they asked for, is LW, length times width, which would be 8 times 16. So if we plug that into the calculator, you could figure that out. It's 128 feet squared. Okay, so that's my max area. Okay, and the dimensions then are your width is 8 and your length is 16. Okay, so we solved that problem using symmetry. All right, so that covers it. You should have enough information to now do your problem set, and I recommend that you get on this one pretty quick because there is a new skill you have to learn here, completing the square, and it might take a little bit of practice, and you don't want to be asking questions about it at 11 o'clock at night, right? Because then you might get a little bit stressed. All right, so ask me whatever questions you've got using Remind. That's the preferable method, and I will wait and see if you have any questions.